Right, good evening everyone. Apologies for the slightly delayed start. I completely failed to look at a clock and realize when I was on. So, let's get started. What is an onion? Well, it's one of these. Okay, but really, what is an onion? Some of you may have heard of the Tor network. Some of you have probably even used it. In fact, I'd expect about half the room has probably used Tor at some point in their life. But for those of you who don't know, Tor stands short for the Onion Router, and it is a way of obfuscating and hiding your traffic on the internet by sending it through 3 other machines before it goes where it's intended. This is very useful for the kind of people who would want their activity on the internet not necessarily to be tracked by everyone on the wire. This can be used for illegal things and also other things, but we all know what people really use Tor for. So Tor works like this. You've got some TLS on the outside, so it looks like a normal web browser connection. And then each router has its key inside. So your actual data is encrypted first with the last hop's key, then the next hop's key, and then the key after that, and then shove it inside TLS. And then along each hop, each router removes its layer of encryption. So by the end, you just have your data, but the end has no idea where it started, and where it started can't read anything inside. So no one on the path can correlate your data with who's doing it or what's going on. Tor has this wonderful thing called an onion site, which you've probably seen these. It's like these long string of characters, .onion. That long string of characters is actually a public key and allows you to host a website on a domain name that can't be seized, because every domain name that you buy normally involves some financial transactions, and then it's tied to you via your credit card or however you've paid for it. And of course, then the domain is just an entry in the database. So if someone were to not like you having that domain name or what you're doing with it, then they can just get that domain name deleted from the internet through the standard legal processes. But because onion sites are just public keys, you can't do that. So when you copy this in, you're basically telling your browser, hey, go to the website at that public key. Can't delete mathematics. So the way this works is, you have this public key and you go to one of the directory servers and say, hello, I'd like to get the data that's with this public key. Little side note, you actually get it with the blinded public key, but we'll come back to that later. And then this says, oh yeah, I know about this website. You should go talk to one of these 3 introduction points who will help you get connected to it. Also, here's a signature over it from the website itself, because again, it's a public key, so you can just sign things with the website. Then your went a bit too fast. Right, then your browser goes and connects to one of these introduction points and says, hello, I've set up a connection to this rendezvous point, and I'd like to connect to whatever this site is. The introduction points don't know what you're connecting. You don't know what you're connecting. You just say, I've set up a circuit to this rendezvous point. Please also set up a circuit to this rendezvous point, and then we'll exchange data over there. Then the site you're trying to access does that, and then you have internet. There's a problem with this. There's not that much TLS on these sites. This is really difficult to read the numbers from here, but I can read them from here. So on the clear web, a good 63% of websites have HTTPS enabled on them. Probably more by now, but this was data from November 2023. Only about 30% of onion sites had HTTPS enabled on them, and there's a statistical when a p-value is something like e to the minus 65, that's probably a statistical difference. But you might say, does this really matter? Tor is already encrypted. What does it matter if we add HTTPS on top of this? Well, yes, but HTTP2 just requires HTTPS. HTTP3 does as well, but we can't currently do HTTP3 over Tor because UDP is not supported over Tor. You might want to do something with your onion site that requires interacting with people's credit card data or other financial data, at which point PCI DSS applies, and that requires TLS. Defense in depth. For example, your Tor terminating proxy might not be in the same part of your network as your web server, and it would be useful to not just have plain HTTP running over your internal network or over the internal network of whichever customer is connecting to your website. There are a lot of browser features which can only be used when you have HTTPS enabled. In the Tor browser, most of these are allowed on Tor sites without HTTPS, but if you just want to use Google Chrome or Safari or your standard web browser, then, you can't use the webcam because it doesn't have a TLS certificate. Secure cookies is another useful thing, or content security policies also can only be enforced when you have HTTPS. And the final, more interesting recent bit is Onion Association, also known as sorted onions, where you basically have a TLS certificate with 2 certificate alternative names. So if you want to verify some cryptographic link between these 2 sites, because without verifying externally, you don't know that the second one is actually the Onion site of, say, the BBC. But if you find a TLS certificate that has both of these in, then you can have some relatively high level of assurance that these are in fact operated by the same entity. And therefore, you can safely redirect your users who typed bbc.co.uk into their web browser to the Onion site, and then there is no traffic over the open internet involved, and everyone is a bit more secure. So the goals of the work that I'm discussing here is to define extensions to ACME to automate the issuance of Act509 certificates to Tor Hidden Services in line with accepted methods of the CABF-BR, and non-goals is anything not accepted by that. And now I have some acronyms to explain. So let's start with the CABF. It stands for the CA Browser Forum. And these are the people who define all the rules for what your certificate does and how it's issued. So if you've ever had to get a TLS certificate for your website, you've dealt with the rules of the CA Browser Forum, because they set how this certificate is validated, what's inside it, conditions for its revocation, conditions for its use, what the certificate means in a legal context. We have all these internet standards about the actual encoding of these certificates, but then someone needs to write the legal policy to go with it that actually translates this encoding into things the real world understands, and the CA Browser Forum are the people who write those very long, very boring documents. Their big document that most applies is the baseline requirements, which is something like 500 pages of rules and procedures on certificates. Anyone who has ever had to deal with a CA at some point on the issuing side has had to read this and read this and read this again, and I hate it. It's long. ACME. Right, this is an IETF protocol defined in RFC 8555. It stands for the Automated Certificate Management Environment, and it is that thing that allows Let's Encrypt to work. It's this wonderful protocol for just automatically getting certificates for your website. If you go back 10 years, almost no one had HTTPS on their website because it was a pain. You had to deal with awful web interfaces of CAs. They were slow, it was confusing, you had to copy around all this weird text that started with -- begin certificate signing request. None of this made sense, so no one bothered. And then, you forgot to do this, no, your website's offline whilst you deal with renewing the certificate because it expired last week and no one noticed. So yeah, as I mentioned, this is the protocol that Let's Encrypt created and then handed off to the IETF as to do the maintenance work on it, but this is now widely adopted by most CAs in the world. So I can just get a certificate for my Onion site from Let's Encrypt? Not so fast, unfortunately. So what is already out there in terms of TLS certificates for Onion sites? Because 30% of them did have it, so they're doing it somehow. So in Appendix B of the certificate, CA Browser Forum baseline requirements, you're getting into the weeds when you have to start referencing things with section 3.2.2.4.20. There are the rules on how to issue a TLS certificate to a Tor hidden service. And these are the 4 methods allowed. The first 3 are also allowable for a standard run-of-the-mill website hosted on a normal domain. And then there's a special one which we'll come on to later for explicitly for Tor. And this is the one that's really the key to making this work well in ACME. So current state of CAs is DigiCert will issue you an EV cert only. EV certs are extended validation. They involve like a notary public, which is, for those of you who don't know, a special kind of lawyer. If you have to get a lawyer every time you have to renew your TLS certificate, would you really be doing HTTPS on your website, or would you just say, no, this is way too much effort and give up? Harika, which is the Greek Universities Research Association, they will issue you a normal domain validated certificate, like the normal ones you get on every website. But neither of these have any automation, so you're still kind of stuck at the copying text files around, dealing with confusing web interfaces at least once a year and paying. So we can see the impacts of DigiCert only issuing EV certs, because on the open web about, 1.07% of websites have EV certs, but of Onion sites it's closer to 10%. So let's actually try and automate this. So how does ACME actually work? It's a relatively simple, HTTP exchange between you and your browser. There's some signature stuff in there, but that need not concern us at the moment. You say, hello, I have an order, and that order is, I would like a certificate for this list of websites valid from this time. And the CA says, cool, I've got your order. You need to perform these authorizations, and then I will issue your certificate. Normally this is like, you need to put this file up on your website. If you've ever seen requests in your log for like .wellknown/acme challenge/some random string, that's one of these authorizations to check that you are actually the person in control of that website. And then you say, okay, cool, I've done that. The CA goes and validates it, and then says, yep, cool, you've done it. Please give me the public key to sign. And then you send the CSR, which is your public key. And then the CA goes, okay, I've got it. Give me a minute, I'll go make your cert. And then says, okay, your cert is ready. And then you download it and put it on your web server. And this is all designed in a way such that a cron job can do this once a month and keep your certificates up to date. And you don't have to worry about anything. It just sits in the background, does its own stuff. It's wonderful when it works. It's horrible when it doesn't. So one of the things that goes in the order request, as I said, is what do you want the certificate over? This is called an identifier type. Now, most commonly, this will be type DNS, which is a DNS value. And there was some debate in the standardization process for this about whether a .onion counts as a DNS identifier type. It was eventually decided that yes, it does, because then a client can not really care about the fact it's dealing with a different kind of website if it's using the HTTP1 or TLS ALPO1 validation methods, which are effectively the you put this file here. If you just have a client that knows how to put a file in a folder and tell Nginx reload, you've got a new cert, then if that website just happens to be accessible over an Onion site, it doesn't need to worry about that, because it just says, oh, that's a weird domain name, whatever. Hello, CA, can I have a cert for that? And then the CA deals with the slightly more complicated side of it, but the client doesn't need changing if you just treat it as it is DNS, even though it's not in the DNS. Then, this different validation method that I said I'd come on to. So this is a clever one, because clients prove control over the Onion domain by signing a certificate signing request, try saying that 5 times fast, with the key of the Onion domain. Because, as I mentioned, Onion domains are just public keys. So then, if you can sign something using the private key that corresponds to that, like a nonce, for example, then you can prove that you actually do control that public key, and therefore you control the domain. You send a CSR that looks like this. This is something every website will do when it requests a certificate, but this one is slightly special because it has the 2 extra things that OpenSSL can't render, which are those OIDs that end in 42 and 41. Those are 2 random values that the you generate and the CA generates, and the public key in this case is not just the public key of your certificate that you want, but it's the public key of the domain name itself. And then because you've signed that over those random values using the domain name itself, then you've proved, oh, okay, you do actually control that domain. So great, we're done. Okay, there's more to it. There's always more to it. So CAA is the Certificate Authority Authorization. This is a wonderful security mechanism that helps you mitigate the possibility of misissuance. If you know that you'll only get a certificate from DigiCert or only from Let's Encrypt or only from Google, then you can say, hey, no, every other CA, you're not allowed to issue certs for this website. You can even go as far as say, hey, Google, you're allowed to issue certificates for this website, but only on this account. No other account can do it. And then this is a really useful mechanism to stop a configuration mistake from allowing someone else to get a TLS certificate for your website. And given how the Tor network is supposed to be this secure thing, this would be useful to implement as well. So these go in DNS records that look like this with issue and then a CA identifier and maybe some other flags and fields on it. But there's a problem. Onion domains aren't in the DNS, so this doesn't quite work. Instead, we put the CAA records in the bind zone file format in the second layer hidden service descriptor. And once again, I have more explaining to do. So if we go back to this slide from the start with this list of introduction points that you send to the directory server, this is the hidden service descriptor. It's just a text file. And it looks like this on the outside. There's HS descriptor at the start, so you can identify, okay, I have got the right kind of file here. Some lifetimes to expire it, just in case the server goes offline, then this will eventually disappear. Some certificates, and then this super encrypted blob. And this is encrypted with the service's blinded public key. What is a blinded public key? It basically means the directory authorities can't see what's inside because you generate the blinded public key from the actual public key, and that's a one-way operation. It's effective. It's they're ED25519, so you just do another multiplication on the elliptic curve and get another public key that you can derive from knowing the previous public key, but you can't go the other way. So you can go from the service's public key to its blinded public key, but not back, and the same with the private key. So then the directory authorities can't actually see what they're seeing, what they're storing. All they see is this thing which has a version number and expiry. Not much useful in there. But if you're connecting to the website, you've already typed in the domain name, so you have the public key, which means you can get the first layer encrypted data, which then has this auth client stuff, and then another encrypted blob. And then inside this is the actual information you needed with all the introduction points. The reason there's the second layer thing is auth client can be used to say, okay, only these people who know this shared secret can actually access this website. And if you don't, then you just can't decrypt the second layer data and can never get the introduction points. So because this is just a text file, we can just shove the CAA records in there. Job done. As a bit more, so what if we're using auth client? Then we need to somehow let the CA actually access these CAA records so they can check them. So we add another bit into ACME that has the CA's public key, so that then that can be added into the auth clients lists so that the CA can actually read them. And there's one more final bit, which is that the first layer, which is accessible to anyone, has this extra flag of CAA critical, which is just a signal that this service might be using authorized clients, and there are CAA records in here. So if you can't decrypt the second layer, you shouldn't continue with issuance. Otherwise, a CA that wasn't authorized to issue obviously wouldn't be in the authorized clients and then couldn't read the CAA and then couldn't see that it's not authorized to issue. So why would we even bother with this? Well, consistency with how the rest of the DNS works is nice. It reduces the chance of misissuance, although that is already slim with Tor Onion because of the whole extra cryptography that exists on top of it, different from the DNS. It allows you to enforce organizational policy, which is not really useful to individual operators, but in larger companies, that's very much appreciated. And the other final neat thing a CAA does is you can publish an IODEF, which is the instant object description event format, I think. And basically, that's an email address or a HTTP endpoint where you can receive notification of security incidents relating to your certificates. Again, useful things to have. So there are some implementation challenges with making this work. CAs need to run a Tor client if they want to issue certificates for it. They need audits for that Tor client because all of a CA's code needs to be audited, and a client needs to be, certified memory safe so that a bug in Tor doesn't crash the entire CA. This was a problem especially raised by Let's Encrypt, who write all of their code in Go, and they were like, Tor is written in C, and we're not so sure about running this code in production, which is fair. So for HTTP01 and TLS ALP01, there's unfortunately no way around this. If you want to check a HTTP request to just check that this magic file has been put there, then you have to make a full Tor connection. There's no way around this. But with Onion CSR01, we can be a bit clever. So we can just put the CAA over ACME. Why does this even work? So Tor directory authorities are already untrusted in the security model of Tor. Everyone in Tor is assumed to be a hostile actor, so are the directory authorities. And the hidden service descriptor is verified purely using the service's public key. So if we just send the data the CA needs anyway, signed in the same way that it would be signed in the file that they could pull from the directory authorities, then the same security guarantees apply, and the CA never has to make a connection to Tor in the first place to issue your cert. So in this final bit, you just add some extra Onion CAA stuff to your request with just the CAA lines, as they would be in the hidden service descriptor, and a signature over them. Or rather, a signature over Onion CAA pipe, an expiry pipe, the CAA. That's to mitigate any possibility of cross-protocol attacks. So this is all nice and good, but how do we actually make sure that this is an internet standard? How do we get an RFC number assigned for it? There's a 24-step simplified process here, courtesy of Ben Jojo, which I will now try and briefly explain. So when you have an idea and you want to make it into an internet standard, you first make a draft of it, which is just you write it up in a document. This will probably be wrong, it will probably have mistakes, but you need to start somewhere. You then upload it to datatracker.ietf.org, which is where all the documents go, and then you email the working group. The working group is the basically self-selected group of experts. Anyone can join a working group, anyone can join the mailing list, anyone is allowed to have an opinion, but it's generally the experts on this in the field. And then you just keep emailing in circles, updating the draft until everyone's fairly happy that this is a sensible idea. Then you go to an adoption call, which is, does the working group think this is worthwhile spending the working group's time on? And usually, if you have a half-decent idea, this will be adopted. Then you keep discussing, and you keep refining. This goes on for months. Then, when the working group thinks it's got it right, it goes to a last call, which will inevitably be when someone says, no, you've done it wrong, you need to change this bit. And then there's some more discussion, and then it just keeps going and going and going, and hopefully then at some point, no one says, I don't like this. And then the working group has officially approved the document, like, we're done with it. Then the working group assigns a document shepherd who makes a write-up about what the document is, what it does, what discussion has happened on it, and hands that over to the IESG, which is the Internet Engineering Steering Group. And these are 14, I want to say, people who have effectively the final say on what becomes an internet standard. They're not there to check the minutiae of the document, they're just there to give it a once-over and go, yeah, this seems like it's been discussed properly and is sanely thought out. And then they can say, they have a ballot, they all vote, and they either say, nope, go back, do it again, start again, and you go back to step one, or they go, yeah, this looks about right. Then it goes to the RFC editor, which then sets it out, typesets it nicely, then it gets published. And this process has taken two 2.5 years for me to get through for this one relatively simple change to an existing protocol. If you have an entirely new protocol, it's not uncommon to spend 10 years discussing it before it gets finally published. So where are we now? There is this document. You can see all of these revisions that it's gone through, and then all of these reviews from various members of the IETF community, but it has been approved. It is currently sitting in the RFC editor's queue, and it has been there for 10.3 weeks when I made these slides 2 days ago, and it's being edited down to its final version. At some point, I will get an email from the RFC editor saying, we're done editing, are you happy for us to publish this? This should happen in roughly about 5 weeks. It takes, on average, about 12 weeks for the RFC editor to edit something down. They're very busy. So, if you want to play with this, there's a reference CA that will issue non-publicly trusted certs for your Onion sites at acmeforonions.org. There's a certbot plugin that does the new Onion CSR01 stuff, just called certbot Onion. You can install that with pip, and it should magically work. Thank you. I'm sure you have questions, and the slide deck is available on my website.
So since you said that you are currently the only person running an ACME for Onion CA,
Yes.
has there been issues of people trusting that CA because it's the only CA that currently does this?
Yes, I have had people emailing me asking, how do I add this CA to my browser? And then I have to respond, no, please don't do that. That's a stupid idea. This is running on a server in my flat. Do not trust this. But I have had people use this for what they think is legitimate certificates for their Onion site. It's not been many people, but it's been enough to make me slightly concerned.
Any more questions? Okay, if not, then thank you, Q.
Well, feel free to corner me afterwards. I'm always happy to talk.